Hi everyone, and welcome to my flight mechanics class. So the first thing that I'm going to clear out today is what exactly is flight mechanics. It is the discipline which analyzes and predicts the behavior of air vehicles under the influence of propulsive, aerodynamic, and gravitational forces. In this class, we're going to cover the motion which results from these forces and describe it mathematically with equations. The good thing is, if we do understand the dynamics, then we'll be able to control it, as a prerequisite to a control system is going to be a dynamics model. As a reminder, air vehicles move about in the atmosphere with 6 degrees of freedom. That is 6 independent ways of moving through three-dimensional space, and this is going to be a natural split in our equations of motion, as we're going to have the equations of linear motion, that's 3 degrees of freedom, and the equations of rotational motion, that's an additional 3 degrees of freedom. Together, they form the 6th equations of motion. Now, these equations are going to be split into two parts. On one side, you're going to have the sum of the forces, or sum of the moments, while on the other side, you're going to have the air vehicle's response, and it is going to be equal to the time rate of change of linear momentum for the sum of the forces, and the time rate of change of angular momentum for the sum of the moments. So the first building block leading to the equations of motion that you need to understand is the different reference frames or axis systems used in aerospace. If you remember, when you were in middle school, you started with two-dimensional reference frames, x and y, and then moved on to three-dimensional reference frames, x, y, z, and essentially what you're going to have here are several x, y, z's. And the reason for that is because motion is relative. Depending on what you use as a reference, your velocity and acceleration, and more precisely their components, will be different. So that needs to be precisely defined. Depending on which book you use as a reference, the convention used for the reference frames may vary a little. Some books may define the EOMs in the wind axis system, while others will define them in the body axis system. Some books may define the aerodynamic forces in the stability frame instead of a wind frame, while some books may define motion in the vertical plane only with the 3 degrees of freedom EOMs instead of a 6th EOMs. So I was a little confused at first, as I thought that all books should give the same result, but actually it boils down to how accurate or how simple you want your model to be. It is all about which assumptions or which simplifying assumptions you make. For the purpose of this class, we're going to pick one convention, and it is going to be based on Introduction to Aircraft Flight Mechanics by Thomas Hitchhout. Now, in this book, we use 3 different reference frames. There's the inertial frame, the body frame, and the stability frame. The inertial frame is often referred to as the northeast down frame, or earth frame. It is the only frame in which Newton's second law, F is equal to ma, stands without any adjustments or additional terms. A number of assumptions need to be made for that reference frame to be considered inertial, and that is that the Earth is considered to be flat, non-rotating, non-accelerated, and the frame is fixed to a chosen point on the ground. As its nickname implies, the x-axis points north, the y-axis points east, and the z-axis points down to the center of the planet. It is probably the most important reference frame, as everything is going to be relative to the inertial frame. The next frame is called the body frame, and it is fixed to the body of the air vehicle being analyzed, with its origin at the center of gravity. It moves and rotates with the air vehicle, so whatever the aircraft does, the body frame will do as well. It is the most common frame to define the equations of motion, and that means that any vector that is not defined in the body frame will have to be transformed from its original frame to the body frame. As you can see, the x-axis comes out of the nose, the z-axis is perpendicular to the x-axis, and the y-axis forms a right angle with the xz plane. The last frame used here is going to be the stability frame, and it is essentially a body frame rotated by the angle of attack alpha, and to be more accurate, by minus alpha. It is used to define the aerodynamic forces, and is an idealization of a wind frame in that it only takes into account alpha and not alpha and beta of a side slip angle. If beta were to be present, you would have to project the velocity vector onto the plane of symmetry of the aircraft. As you can see, the x-axis points into the projection of the velocity vector onto the plane of symmetry of the aircraft, and that essentially means it is concerned with where the relative wind is coming from. So the reason why we have so many different reference frames is because some vectors are more conveniently defined in some reference frames, and different vectors are more conveniently defined in other reference frames. So here we have the weight vector, the aerodynamic forces vector, and the thrust vector. So the weight vector is defined in the inertial frame or airframe. The aerodynamic forces vector is defined in the stability frame, and this is actually an idealization because in many books it will be defined in the wind frame. And finally, the thrust vector is going to be defined in the body frame. Now, the reason why the z component of the weight vector is positive is because of what you see here. The positive z-axis points down to the center of the planet, and because the weight vector points down as well, it is actually positive. For the aerodynamic forces vector, it is the same method and the same rationale. You see that the lift is negative because the positive z-axis points down, and I've actually taken the liberty of assuming that alpha is equal to 0 to idealize the situation and make it more obvious, and you can see that the lift points in the opposite direction of the positive z-axis and is therefore negative. For drag, it is also negative because it points in the opposite direction as the positive x-axis. In terms of the thrust vector, it is angled with respect to the body x-axis by the angle phi of t. And the reason why the z component is negative is because in this book, it is assumed that the thrust vector is pointing up in relation to the x body axis, and the projection onto the body z-axis is pointing in the opposite direction as the positive z-axis, and for that reason, it is negative. Alright, this is it for today. Thank you very much. See you next time.